Okay, in 4.2 we're going to look at the trigonometric functions. And to understand that, the value of using trigonometric functions lies in an understanding of the properties of similar triangles. And so, understanding similar triangles, and here are two similar triangles. The properties of similar triangles are that corresponding angles are equal and corresponding sides are proportional. So what do we mean by that, just to go over that? So if these are two similar triangles, basically the idea is that one is a larger version of the other. And so all of the angles will be equal. So for example, this one looks like I've got a 90 here and here. So those angles will be equal. The corresponding angle to this one in the other triangle will have the same size. So those two will be the same. And then the third one will be equal. And if that's the case, then what we have is corresponding sides are proportional. So how do we determine corresponding sides? Well, corresponding sides from one triangle to another will lie between the same two equal angles. So for example, this side here, let's call it A. A1, because it's in the smaller triangle, triangle number 1. And triangle number 2. So A1, this side A, lies between the 90 and this smaller angle. And therefore on this triangle, the corresponding one lies between the 90 and the same equal angle. And so we will call this A2. Following that pattern, the side between the 90 and the next smallest angle, or the medium-sized angle, let's call this B1. And therefore, on this one over here, the corresponding angle is B2. If I make a ratio of one side to another, for example, A1 over B1, that ratio is equal to the ratio of the corresponding angles, or sides, in the other triangle. So A2 over B2. And again, we could also do C1 and C2. Right? Forget that part. There we go. That would involve another set of ratios. So anyway, yes, corresponding sides are proportional. If I take this ratio, I will do the division. We will get a decimal value that will be equal to this one. So in a sense, lowering them down to their lowest form, they equal the same number. And that's the basis of the trigonometric functions. So let's look at similar triangles in a little bit different way, a little more like what we started to look at in 4.1. If I draw a terminal arm, so I've had a rotation of an angle theta here from the x-axis to the terminal arm. Is my theta right in here. That terminal arm is defined by plotting, a particular point out here, connecting it to the 0, 0, the vertex, and we drop down a vertical. So it creates this right triangle with a right angle where the x and y values meet, an angle theta rotating in this direction, and a hypotenuse, right? Let's call that point P1. If I go a little further out that terminal side, P2, and do the same thing, would you say, or do you agree with me when I say that I've just formed two similar triangles? We have a smaller one, the first one bound by the red dotted line with P1 as a point out here. It's got equal angles to the other one that is bound by the P2 point with the green line because they both have this 90-degree angle. They both contain theta, so that must be equal. And they both contain these two angles, which would be equal as well, because the dotted line for P1, the dotted line for P2, those are parallel lines. This could be considered like a transversal going across, forming two equal angles. So we have three equal angles and therefore three corresponding sides. So the ratios of corresponding sides will be equal. We can do the same thing even further, you know, to stretch this along and go further out. P3, make a bigger triangle, and the same thing's going to happen, right? So rather than talk about this on the very large scale, we just break it all down to the smallest scale possible. And that's where we will look at this whole idea. Oops, I'm still in purple. Well, we'll do the axes in purple, and we'll do the rest in another color. Let's go back to black. And draw. All right. That looks good. So keeping this just to the bare minimum, right? We'll drop down the perpendicular. So this triangle has an x value. That is the distance from 0 to here. It has a y value. That is the distance that we travel up the y-axis, which would be the same as this mark right here. And it has a hypotenuse, r, which is opposite the 90. Our angle theta sits between the x-axis and the terminal arm. We're always measuring off of the x-axis. So now, if we look at the ratios of a few different sides, for example, if I take the y value and put it over the r value, so y over r, that's one ratio of sides. And in fact, if you've seen some trig before, you might recognize that according to theta, or with respect to theta, y is its opposite side, and r is the hypotenuse because it's opposite the 90. So that's actually equal to something you might have seen before, opposite over hypotenuse. And that is called the sine of theta, okay? So with respect to theta, the opposite over the hypotenuse is the sine of theta. That ratio is the sine of theta. And in this type of a labeling, where we are on the Cartesian plane with the xy axis and our r, then we can shorten those names to y over r, but they're exactly the same as opposite over hypotenuse. Now there are two others that we need to know. The cosine of theta, and you may know that as adjacent over hypotenuse. Have a look at the diagram. With respect to theta, the hypotenuse is still the r, it always will be, and the x is the adjacent side, so that's actually x over r. And the tangent of theta is another possible ratio we can make with these sides, which is the opposite of theta over the adjacent to theta. So opposite over adjacent, which is, in this case, y over x. So I've got all possibilities, except for the reciprocal of each, okay? These we refer to as the primary trigonometric functions. All right? If you're unfamiliar with them, this is something really to get used to. If you know them as the sides as opposite, adjacent, and hypotenuse, then don't forget that. There's still, you know, so, ka, toa to remember. This will come in useful still. I'm just changing the naming for when we are working within the Cartesian plane to give this a little bit different discussion, because what we're going to do later, we won't be staying just in quadrant 1. We're going to move around the Cartesian plane into quadrant 2, 3, and 4. Okay, so we'll be rotating later when we get into chapter 8. For now, we're going to stay in quadrant 1, but I am going to change this naming to the X, Y, and R names. Alright, so those are the primary trigonometric functions. There are also 3 secondary trigonometric functions that are not used as often, but it's still important that you know that they exist and what they are. So let's have a look at what those are. The secondary trig functions. Oops. All right. Those secondary trig functions are actually the reciprocal of each of the 3 primary trig functions. So each one has a corresponding reciprocal function. The reciprocal for the sine of theta is called the cosecant of theta. And its short form is CSC, cosecant. So that is cosecant of theta. And that is the reciprocal. So instead of opposite over hypotenuse, it becomes hypotenuse over opposite, which then is r over y. The reciprocal function for the cosine of theta is called the secant of theta. Alright, so secant. And that is hypotenuse over adjacent, which is actually r over x. And the reciprocal function for tangent is cotangent of theta, which is the adjacent over the opposite, or x over y. So, right, so cotangent. There they are, the 3 secondary trigonometric functions. Now, one way to keep them straight, and I put them on a formula sheet for you, but just to keep them straight, or something that might be helpful for you to keep them straight. Cotangent and tangent, they naturally sound like they probably match up and go together, right? Now these other ones, sine, the one thing I would say is sine starts with S, its corresponding reciprocal function does not. Cosine starts with C, its corresponding trigonometric function does not. So there's really kind of this crisscross thing going on with C and S, and I just use that to keep it straight. It would be nice if they matched up, but they don't. So anyway, that's just something that might be helpful for you to keep them straight. But they really are just the reciprocal of the corresponding primary trigonometric function. Okay, so one of the things we want to kind of make clear is that an angle is uniquely determined by the point, a particular point along the terminal arm that exists. Okay, so amount of rotation is determined by the terminal arm, and the terminal arm passes through many points x, y along here. So for example, plot the point 6, 8. Okay, remember that is x, then y. So if we plot the point 6, 8, this is 6 here, this is 8 up here. This point right here is the point 6, 8. Therefore, this triangle has a length of 6 here, a length of 8 in the y, and this is our r. This is our theta measured from the x-axis with the rotation going this way, positive theta. All right, if I wanted to write the 6 primary trigonometric functions of theta, we've got our y and our x. We don't know r. How do we calculate r? All right, so calculate r. R is the hypotenuse. So just like the equation for the Pythagorean theorem, c squared equals a squared plus b squared, it's the same relationship here. R squared equals x squared plus y squared. or solving for r, square root both sides, the square root of x squared plus y squared. So to calculate r in this case, r is equal to the square root of 6 squared plus 8 squared, which is the square root of 36 plus 64, which is the square root of 100, which is 10. Now I know there's also a negative 10, which is a root of 100. We are going to consider r is always positive. So take the positive root when you do this. I've got a nice perfect square here. It doesn't always turn out that way. You might have to use some decimal values if it doesn't work out beautifully. I would caution you from just rounding to a whole number if it's not a whole number, okay? Use decimal values in this case. So let's write out the 6 trig functions that are determined by this point 6, 8. So sine theta is y over r. So we take our y value, which in this case is 8, put it over our r value, which is 10, and we have our sine theta, which is, if we change it to a decimal, 0.8. It works out beautifully. If this wasn't as precise as that, then I would recommend more decimal places, but this one only goes to 1 and it stops right there, so that's nice. So trigonometric functions can be as a fraction, a reduced fraction, or even as a decimal. So cos theta, what do you think that is? Cos theta is x over r, so that should be 6 over 10. As a decimal, that is 0.6. And tan theta is y over x, which is 8 divided by 6. As a decimal, that is 1.3333. Okay, so I'm going to clear the screen, and then we're also going to do the secondary trigonometric functions for this. Okay, so the secondary trigonometric functions then are the reciprocals of each of the primary trigonometric functions, which are here. And if we take the reciprocal of each, so the reciprocal of 8 over 10 is 10 over 8. Or as a decimal, the reciprocal of 0.8 is 1.25, and that's the cosecant of theta. For the secant of theta, the reciprocal of 6 over 10 is 10 over 6, and as a decimal, that is 1.66 over 67, right? And the reciprocal of tangent is cotangent of theta, which will be 6 over 8, which is 0.75. So, there are different ways to get reciprocals. Take a look at your calculator. Maybe you did some of this in chapter 1 where you're finding reciprocals. You have a button that is x to the minus 1, or one that looks like 1 over x. You could put in 0.8, do the reciprocal of that, and you will see that it is this decimal value. Another way is to just take 1 divided by 0.8, and that equals 1.25. Right? The other is to do 10 divided by 8. That gets 1.25 also. Okay? Now, lastly, in this section, we might be concerned with what is the angle, and there's a correct way to solve each of these equations. They all refer to the same theta, so we should be able to solve all 6 and get the same angle. I will show you how to solve one of them. You can maybe practice with the other 2 of the primary. So let's look at the sine function. If sine theta equals 0.8, how do we find theta. This is a function of theta. This is not sine multiplied by theta. It is a function of theta. So it's a little bit different than just dividing by sine, which is not possible and doesn't make sense. So the correct way to rearrange this mathematical sentence to solve for theta is to say then theta is equal to sine inverse of 0.8. And if you look at your calculator where your sine button is, the second function of that button says sine to the minus 1. This is the inverse function of sine. So when you put an angle in here for theta in your calculator, it gives you the sine ratio. You can also ask the calculator for the angle that has a sine ratio, in particular, in this case, of 0.8. So type in your calculator your inverse key or second function key. Sine, you have to use the right trig function going with this value, and 0.8. And you will see that the angle is, let me just do that on my calculator, 53 degrees. I'm just going to round that to a whole number. It has more decimal places, but let's call that 53 degrees. All right. If you do the same process with these two, you should also get 53 degrees, and I urge you to practice that and make sure you understand this with your calculator. Now, that is all for 4.2. Thanks for watching.